Hi guys, how's it going? So today we're going to go through this question called all path from source to target. So essentially we're told that we're given a directed acyclic graph of n nodes labeled from 0 to n minus 1. So we need to find all possible paths from node 0 to n minus 1, and we need to return them in any order. The graph is given as follows. Graph I is a list of all the nodes one can visit from node I. There is a directed edge from node I to node graph ij. I know that was quite mouthful, but in simple terms, what they're saying is that if we're starting here, we can go to 1 or we can go to 2, and from 1 we can go to 3, and from 2 we can go to 3. So you can think of 0 as the source and 3 as the target. So we need to move from source to target. So we need to find multiple ways we can go there. So from an array perspective, how this thing works is that you can think of this as 0, right? As 0, as 1, as 2, as 3. So because we know we start at 0, where can we go? We can go to 1, we can go to 2. So if we go to 1, we can go to 1. So 1 tells us to go to 3. We can go to 3. So in our array, essentially we're going to have 0. We started at 0. We went to 1. We went to 1. We went to 3. We went to 3. So we're going to include that guy. So starting at 0 again, we can go to 2. Let's go to 2. And we use a different color. Go to 2. This is the 2. 2 says go to 3. We go to 3. So how did we do it? We started at 0. We went to 2. And we went to 3. So as you can see, the results that they got, these are the results that we have. Okay, so how can we go about this, guys? So we definitely know, I'm just gonna write an example because I wanna be able to keep track of it as I'm explaining. So we can have 1, 2, and we have 3, and we have I think that is 3, and we have an empty box. So one way we can think about this, because we know that here we have indexes 1, 0, 1, 2, 3. So one we can say, okay, let's have an index to say start, right? Then what we can do is that we can now go through the element in our array for neighbors, right, in graph. And what we do here is that we pass that thing called start. So essentially this is going to give us the first array, like 0, right? Then when we get the first array, we can then say neighbor, because we know that this is going to be an array. We essentially get the first element from this, right? Then we have an element that we're going to get. In this case, we know we're going to get 1. Then what we do with 1 is that we append it to our results. Initially our result is going to be 0 because we're starting at 0, right? Then we say, okay, cool. Results dot append, okay, append element, right? We know that element, it is 1 because we said give us the neighbor of 0, it's 1, right? So which means that here we're going to increment, this is going to be 1, right? Then when we are done, what we do is that we update our start because we want to go to what 1 was. So it's going to be start point to element. Okay, you can tell now start is going to be 1, then 1 is going to be to 3. Then we're looping now 3. We get element 3 and we upload it here. Then we upload what? We upload 3. Like that, like so. Because remember that we updated start with 1, right? We updated 1, then 1 took us to this element. We got 3 when we did this, then 3 we uploaded it. So we have 0, 1, 3, which is correct, right? Because this is what they had. Here, this is what they had, right? But you can see the problem with the solution. How would we then go for 3? Go for 2, right? How would we then explore 2? We just explored 1 and we selected a specific index. So there's multiple index in there. It could be 1, it could be 2, it could be 3, because a node can point towards different paths. So we can have different paths, can go there, can go there, right? So our solution is not robust enough. So this thing here wouldn't solve the problem. We need a way to be able to explore all the paths. We need a way to be able to explore all the paths. So how can we go about it? One way we can think about it is that, yes, we can store the start inside a queue, right? So what we do, a queue is going to actually help us to store all the things that we need to explore. In this case, in this solution, you can see that we were not able to. We can only explore the first element, but now we want to explore all the elements inside a specific node, like 0. We want to go to 1, we want to go to 2, just like that. So now I'm introducing this queue so that it can be able to store those things that we want to explore, okay? Then what I'll do is that I'm going to keep a while queue, right? And I'm going to take that guy that is inside here because I want to take him out so that I can explore this guy. So I'm going to say queue.pop 0, okay? Then what I'll do is that this will actually give me element that is inside there. So I'm just going to say for neighbor, right, in graph, I want to take the last element that is added inside there. So I'm going to take temp minus 1. So here I'm actually going to store these elements here as arrays. So every element that goes in here is going to be an array. Why are we storing it as an array? Because we can have multiple paths. Don't forget about that. And we want to get the last element because the last element tells us where we want to go, right? So for now, we know that 0 tells us where we want to go. So what does the 0 tell us? We pass it into the graph. We go to this, it tells us, yeah. So we know that, okay, we pass 0, we're looping through these two things that are inside here, okay? So you see I created a for loop. So we have 1, we have 2. So here I'm gonna say queue.append, okay? I'm taking the temp, which is currently 0. I'm gonna add the current neighbor. So I'm gonna say neighbor, add this guy. So now, in our queue, we're going to be having what? We're going to be having 0 and 1. Okay? We go again, our loop goes again, because remember that there's 2 elements at index 0. Our loop goes again, it gets 2. It appends it again. It says temp plus our neighbor. So it's going to append 0 and 2. So now, in our query, we have 2 elements, 0 and 1, 0 and 2. This is good, right? So we then say queue.pop 0. Queue.pop is going to pop, because now we have these 2 elements, it's going to pop this one. So 0 and 1. I'm using -1. Yes, I said I'm using -1 because the last element tells us where to go. We know that this 1 is going to tell us where next to go. So that's why I'm using -1. So I'm saying for neighbor in graph, 1, where is 1? We go to our thing. 1 says go to 3. We say, okay, cool, this is nice. So we take the temp, which is 0 and 1. Currently it is 0 and 1. We add 3 because we know neighbor is 3 because we just went to it. So we get 3, like so. We are appending this into our queue. And we're going to continue now because if we pop this, we're going to go to this. But this is what is interesting. You can see that this is familiar. This looks familiar. Can you see this? Yes, it looks familiar because it was these results here. And the good thing is that because we had 0 and 2, we already started. It's going to get popped also. Remember that we pop in the last. We pop this. Now we're going to pop 0 and 2. We're going to do the same. We're going to go to 2. And now we're going to end up having 0, 2. When we go to 2, what do we get? Yes, when you go to 2, you get 3. So you're gonna get 3. It's gonna be in a queue. This looks familiar. Yes, it does. This is here. You see? So now, how do we then return these results? Right? So we can, because we have a lot of things that goes inside a queue, right? How do we know that this is the one that we want? So definitely we're gonna have a results. And one thing that I can tell you is that we can have a target here, and we can ask if the temp, right? The temp last element, so the temp -1, yes, the temp -1, the last element must be 3, yes, because that's our target. That's when we know that we are fine. So we're gonna say, if that's the case, then we're gonna say res.append temp. See, so that's it. O of 1, and the space also is, or not O of 1, O of n, the temp complexity, and O of n space. So that's how we should go about it. So without wasting any time, let's call this thing up. So yeah, we said we're just gonna start with 0, like we said. So oops. So we're gonna have that. Then we're gonna have, I just need to keep track of the results, because just need to return them, because they said that return all possible paths. So I just want to append all the array inside here. Okay, then the target we know that it's going to be the length of the array -1, right? Length of the graph, then -1, right? So we know this because it's going to be the length of this -1, because it's going to be 3. Then what we want to do is that we want to say while, like we showed you the whiteboard, while q. So we want to say temp equals to q dot pop. We're gonna pop the first last element. So here you can use dq. What is it? Yeah, dq, because this is gonna be of n. So it's not gonna be good. So use dq to get temp complexity of O of 1 for getting that, for popping that element. So just for simplicity, if temp -1, this is equals to target, right? So what I want to do is that I want to say res.append temp. Right, so now I'm gonna explore all my neighbors. You know what, I'm gonna write n in graph, then I'm just gonna say I'm gonna filter this by temp, the last element that it to be added. I just want to say q.append temp plus n. I'm gonna put this n inside an array. So when I'm done, I'm gonna return our results, and this should do the trick. So yeah, I think that's the solution, guys. Really appreciate it. Thanks, guys.